It's a real honor to be here today to tour both the Institute and the Foundation here. And it's a pleasure to tell you about a 30-year-old quest and the surprising outcome that quantum physics saved the day in allowing us to be able to make a tabletop X-ray laser. We did not expect that to be the solution, but as is often the case in science, the solution is often in the completely opposite direction that one's intuition initially might suggest. And the other surprise is that it turns out that these light sources are also, just very beautifully suited for some current challenges in nanoscience and nanotechnology. And I'd like to disclose my affiliation both with Jilla and with a spin-off company. It turns out that as we understood the quantum physics and we wanted to make applications, because it was a new technology, no current industry was interested in commercializing it, and so we had to do it ourselves. It was the only way forward. Okay, so let me give you some perspective. 2010 was the 50th anniversary of the demonstration of the laser. We had, fabulous celebrations, and but when the laser was first demonstrated by Maiman way back in 1960, it was called a solution looking for a problem. People had no idea that the laser could be used, to power the internet, to do surgery, welding, holography, a lot of science, data storage, just so many different things. And in that 50 years or so, the wavelength of lasers that are in widespread use have moved from the red region of the spectrum, which was the ruby laser that Maiman first demonstrated, to a wavelength of 193 nanometers, which are the excimer lasers that make our integrated circuits that we now use. That means in 50 years, we've decreased the wavelength of useful lasers by less than a factor of 4, which is actually remarkable in and of itself, because in every other, most other areas of science, in imaging capabilities, data storage capabilities, computing capabilities, we've increased our capabilities by 9 orders of magnitude in many cases. And so it is surprising that the solution is not at all based on a population inversion, which is what we do when we make a laser, but rather on these quantum light source technology. So of course there are X-ray sources in widespread use. Whenever you go to the doctor or dentist, you'll get an X-ray of your tooth or some part of the body if you've got an issue. But it's actually quite remarkable that, when you look at your radiologist or your dentist and they're looking at the X-ray film, it's not a whole lot crisper than that first X-ray that Röntgen took of his wife's hand. And essentially, it's the same technology. Essentially, you're making a picture with an X-ray light bulb. And one way to improve that is to take a picture with a laser, which, as we know, is more focusable, more coherent. So that would be one of the ways forward. So why not build an X-ray laser? So it turns out that it's really difficult. We've known from the time of Einstein what the ratio is between spontaneous decay and stimulated decay. And so you can do a back-of-the-envelope calculation and calculate how much power will you have to put into a system to make a population inversion. Now, when you highly excite a system, it wants to decay very rapidly. Its lifetime is extremely short. And so that means as you try to make an X-ray transition, you're going to have to use more and more power to try to keep a lot of, let's say, atoms in an excited state, or ions. And in fact, the scaling law is brutal. If you do a calculation, the power required scales as the wavelength to the inverse 5th power. And so what that means is I can hold a laser pointer in my hand because in the visible, I only need a pair of AA batteries to power it. But if you calculate how much power you would need to make a 1 nanometer X-ray laser, it would take about a terawatt, and that's about the electrical generating capacity of the United States. So we are not going to make a continuous wave X-ray laser. At best, you'll do transient. And if you want to go to 1 angstrom, it would take a petawatt. And so it was for that reason that the first X-ray lasers actually were observed during the nuclear weapons testing. And in fact, many of us remember the Star Wars era where the proposal was to detonate a nuclear weapon in space and detect a missile being launched using the X-ray laser, or shoot it down. So this was not a scalable technology. And so that is the reason why the first coherent X-ray source was not based on a population inversion or a laser, but rather something called a free electron laser, which was an accelerator technology that conditioned electron bunches so that the X-ray radiation interfered constructively and you got a nice coherent output. And that turned on lasing at 1.5 nanometer at SLAC at Stanford in 2009, 50 years after the demonstration of the visible laser. It lased at 1.5 nanometers, and we were all excited by this as we celebrated the 50th anniversary of the laser. And Steve Chu happened to be Secretary of Energy in 2010. And many of you know Steve knows he has a very good sense of humor. And so what he said was, these X-ray free electron lasers are amazing. You make a millijoule of X-ray power in a 100 femtosecond burst. But they're not free, and I should know it because you had to pay for it. So they cost about $1 billion. So for science, they're amazing. But if you want to have the technology support medicine, manufacturing, or such, you have to find another way also. And so it's very worthwhile to see what part of this could we put on a tabletop scale apparatus. So we have to find a different way. And the surprise, as I said before, is that we can do that using quantum mechanics, because we now know how to control the wave function of a radiating electron using visible lasers. And that's giving us a capabilities we wouldn't, as a graduate student, when we didn't have any coherent sources of X-rays, we would never have dreamt that this would be possible. So we can now make a coherent supercontinuum that stretches all the way from the ultraviolet region of the spectrum to the KeV region, where there's quantum coherence across that whole energy region. We can control the polarization, we can decide if the X-ray beam comes out as with multicolors or a single color, and also make pulses that are shorter than any motion in our natural world. We would really have to go into nuclear dynamics to be able to see processes that are faster than the light pulses we can now make. So how do we do it? So we don't use a population inversion. So instead, we push nonlinear optics to an extreme. And what's interesting just historically about nonlinear optics, that, so Maiman demonstrated the laser in 1960. By 1961, Franken had figured out how to change the color of that laser. So what he did was he took the ruby laser, focused it into a quartz crystal, and the interaction between the red light and the electrons in the quartz material is so strong that you generated the second harmonic, or blue light, and then he used a prism to take a picture, because that's, of course, what people were using before CCD cameras and such. And I don't know if you're familiar with the story, but submitted it to physical review letters, and the typesetter, it was so inefficient that the little speck of second harmonic light, the typesetter thought it was a piece of dust and whited it out. So you can look it up. There is no experimental evidence of second harmonic generation in that paper. And Nicholas Blumbergen, who very sadly actually passed away last week. He, during the APS Centennial meeting, he gave a great talk, and what he said, and they never bothered submitting an erratum, because anybody with a ruby laser, you could focus it onto a surface, into a piece of glass, and you'd get second harmonic, and you would see it with your eyes. So they never, so Franken never bothered submitting an erratum on this. So, okay, so how does this work? So what is happening is that your light field, it's a single color, it's a sine wave. But if you focus it into an anisotropic material, you're driving the electrons with a sine wave, but their motion is anharmonic because the bonds are stronger in one direction than another. If you drive your electron anharmonically, then the radiated field will contain not only a fundamental harmonic, but also higher harmonics of the fundamental field. And so essentially that's allows the polarization, the radiated field will have both the fundamental and second harmonic. So it sounds great as a way to take lasers where you can make them and translate to much shorter wavelengths or higher photon energies. The problem was you could only go so far using this approach. If you tried to make shorter wavelengths, you could make a few harmonics, but the higher orders were dimmer and dimmer. And there's a very nice analogy with sound. If you pluck a string gently, you can get the fundamental tone. If you pluck it harder, you will get higher order the harmonics of sound. But of course, if you pluck it too hard, you break the string. So there's just a fundamental limit on how, and of course you could think in a material, if you focus too much laser light, you just damage the material. And so it just does not work. But it turns out that once we had a femtosecond laser, you can think about a femtosecond laser being able to pluck an atom and do a lot of things to the electrons in the atom before the atoms break. So it's just the perfect nonlinear driver of an atom. And so, interesting enough, back to Star Wars, the Star Wars program funded Charlie Rose in Chicago to figure out what happens when he focused femtosecond lasers into materials, gas, atomic systems, molecular systems, solids. And in 86, this paper was published, that the highest harmonic observed was the 17th in neon. That was way higher than the 7th harmonic that had been seen in all other experiments to date. And then there was some very nice follow-up work out of Steve Harris's group in Stanford, where they saw more than 100th harmonics of light. And not only that, but all the harmonics had the same intensity. So people knew immediately this was not normal nonlinear optics. There would be no explanation for why you would see so many harmonics and why they would all have the same intensity. Nobody knew how they were admitted, but the advice to Charlie Rhodes' group was ignore them, there's likely nothing new. And so Charlie dropped it, and the atomic physicists played around understanding what was happening here. So what's happening, it turns out that it's a fundamental response of all atoms and molecules and solids to an intense laser field that when the field is strong enough, it's stronger than the Coulomb field that binds the electron to the atom. And on each half cycle of the laser, part of the electron wave function can undergo quantum tunneling. And so this is happening every 2 femtoseconds or so. And on each one of these half cycles, a part of the wave function tunnel ionizes. Then, of course, it finds itself in a very strong laser field that's stronger than the Coulomb field. So that just makes that electron move in a sort of a boomerang-like trajectory. So first out, and then when the laser field reverses direction, it goes back. And under the right conditions, this process converts that kinetic energy or wriggle energy of motion of the electron in the laser field into an X-ray photon, and that's happening periodically in time. And so you also get periodicity in frequency, and that is the origin of those beautiful harmonic picket fence that I showed. This is actually what's happening. We know the electron is not a point particle, so this is the quantum picture, where you can think about that the movie starts with the electron, a 2D representation of the electron in the ground state of hydrogen, so the 1s. And then as the laser field gets stronger, you can see there's quantum tunneling, and that's the fundamental laser frequency. But the part of the electron wave function that goes into the continuum acquires a different quantum phase than the part that doesn't ionize, so then you get quantum interferences. And then the spatially modulated wave function, that this could be tens of angstroms wide, now looks as if you're accelerating that electron at much higher frequencies. So the radiated field, we know from Jackson, we calculate the dipole acceleration and take its magnitude squared. And so it looks like instead of accelerating that electron at the fundamental frequency, you're now accelerating it at these very high frequencies. And so this is what gives, this is the actual physical origin of the higher order harmonics. So essentially what the laser field does, it creates a nanoscale quantum antenna that can radiate to very, very high frequencies. I think up to 5 keV might be the highest that anybody has seen to date, maybe about 2 angstroms, from the ultraviolet to 2 angstroms. And it turns out that these, another sort of technological advance that happened just about the same time in 1990, where people were figuring out this response of atoms and molecules to strong laser field. Peter Moulton had developed this beautiful material, titanium sapphire, that still has the broadest bandwidth of any laser. Its bandwidth is so broad that it can support a 10 femtosecond pulse, and it's extremely robust. And back when we were young and assistant professors, we figured out how to build the laser correctly so you could easily make 10 femtosecond light pulses. And that's the perfect driver for these high harmonics, because it only takes about 10 femtosecond to ionize an atom. And so a few cycles of the laser. And so then we had a very robust laser system to drive this process, because in the 1980s, the way we made femtosecond light pulses was either with the excimer lasers or dye lasers. Both of them were, for those of you, they're just very difficult technologies. And so this Ti-Sapphire also really helped with very high energies, very good stable light sources. And so what that allowed our field to do then is to take the fact that we knew how to make atoms emit X-rays, but do that in a dipole intensity distribution, which we know is not a directed beam, but then make bright and directed beams by figuring out how to take the emission from many atoms in a medium, add coherently and constructively in phase, so we could take the dipole emission and then translate that into a directed laser-like beam, which is what we need to actually make measurements. And so to do that, what we had to figure out, what our community had to figure out, is that so the laser light comes in, excites an atom, so you get an X-ray, and then to build up a beam, we need the X-ray light and the laser light to travel at the same speed in a medium, so that the second atom emitted X-rays in phase to add constructively. You might think that that would be very easy to do compared with all this, the quantum, tunneling and such, but it turns out that this is a very hard problem, because as you know, X-rays are not influenced by the medium. They travel straight through and they don't undergo refraction. So our theory collaborator, Carlos Hernandez Garcia, made a little cartoon to show how difficult it was. So he said, imagine the laser is a quantum conductor, and what we're trying to do is get the same number of atoms as there are people on Earth to sing in tune at the same time. Because that is essentially, to make a bright beam, we need lots of atoms contributing, and we need them all to contribute in phase. And the laser light, the wavelength is 4 microns, but the X-ray light we're making is on order of 1 nanometers. So there's a huge disparity in the length scales. There's also a huge disparity in the time scales, because a single cycle at a wavelength of 1 nanometer, as the period is 2.5 attoseconds. The period of a 4 micron laser is on order of 10 femtoseconds. So there's 1,000 times difference in the wavelength and period, and you have to ensure that the different X-ray waves are adding to within a fraction of their wavelength, or you won't add constructively. So that means you need a timing precision of sub-angstrom spatial resolution and sub-attosecond temporal resolution, and we don't have any electronics that can work on these spatial or temporal scales. So the only way to do this is to use the physics, is figure out, can we combine macroscopic phase matching propagation physics with quantum physics, and will they work together? And many of us thought there's no way they would want to work together, that it just was just not possible, because essentially what we're trying to do is we're trying to do a nonlinear optics in a medium being ionized. There's no constant refractive index. So we thought there was just no way to actually achieve phase matching. But it turns out there is, and now we know we can just change the color of the driving laser, change the pressure of the medium, and now we can make laser-like beams over the entire ultraviolet to extreme ultraviolet and soft X-ray region of the spectrum. And we can make these very broad coherent bandwidths. Essentially, if we use a 4 micron driving laser, that has a photon energy of 0.3 eV. If we extend the spectrum out to 1.6 keV, that means we're adding 5,000 order nonlinear process, and we're actually phase matching it. And it is just very fortunate that the quantum tunneling is very deterministic. So the electron is born at a particular time, it recombines at a deterministic time within the laser pulse, and that part of the laser pulse is able to stay synchronized with the X-ray beam. And so it's actually, so that allows us to make the broadest coherent spectrum that has been generated to date, 12 octave in bandwidth, and just this make a very nice beam in the process, and we don't know where the limits are. We have this predictive models that can let us know as we change our driving laser wavelength here from the visible to the near infrared to the mid infrared region, and the red, the lines show our theory that's been validated up to about 4 microns, and the dots are where we've checked experimentally and show that we actually understand what we're doing. And then on the y-axis here show the EUV and soft X-ray and hard X-ray region, and so we've shown that we can make this process work to just slightly under 2 keV. But what we'd love to be able to know is, if we used a 10 or a 20 micron laser, could we then make a 50 keV X-ray beam? Because that would be, you know, a coherent hard X-ray beam, and there would be many applications. But we can't answer that question because we would need to. We would need you know, a theory that could couple the time-dependent Schrodinger equation in 3D to Maxwell's equations with light of very, very different wavelengths and frequencies. And that's just not possible right now, because if you think of that quantum movie I showed, if the a light cycle is much longer, then the quantum diffusion of that wave function is very large. And then you also have the Lorentz force, and so the electron might not actually re-encounter the ion. And so right now, the way we're trying to test the limits is to work with laser scientists, use their different laser systems as they become available, test experimentally, and then go back, develop approximate theories. And so it's a very much just baby steps at a time to see how far we can push this capabilities. And we're continually discovering new things where we thought we were limited in the type of X-ray spectra we could generate. We now know we can play tricks and generate either isolated peaks or supercontinua, and this type of spectrum is useful for different applications. But the very nice thing is that we're getting control over light in the X-ray region by manipulating visible laser light. And for those of you who've used X-rays, this is actually the better way. This is a good way to go, because in the X-ray region, we don't have good optics. We have imperfect lenses. We don't have wave plates. Polarizers are very difficult to use. And so if we are being able to sculpt the X-ray spectrum using visible light is very nice.
How do you measure the spectrum?
That can be done with a simple spectrometer. Yeah, we can also do sort of a Fourier transform if we really want a very, very high spatial resolution. In fact, that's how we measured this particular. So what I show here is the spectrum in the extreme ultraviolet. That here it consists of a set of peaks in frequency, and from Fourier transform, then you expect that's a sequence of pulses in time. In the soft X-ray region, because the phase matching or constructive interference only happens over one half cycle of the laser, even if the laser pulse is long, that is a true supercontinuum. So if you measure how many bursts here, you just get an isolated burst in time. And we did that using a Fourier transform spectroscopy, like an FTIR approach. And there's lots of other ways to do this also. We can actually play with the wave function. So for example, for a long time, people thought you could only use linearly polarized driving lasers because that was the only way for the electron to be ionized and recombine. If you used a circularly polarized driving laser, you could certainly pull the electron away from the atom, but because of the circular polarization, the electron never returns. So we'll just wait one more cycle on this movie. So you see the electron is ionizing, but then it just moves away and actually never recollides, as happens with linearly polarized light. But then Becker's group suggested to use counter-rotating two-color driving lasers, and in that case, you can both ionize the atom and the electron returns. And what that gives us an ability to do is make circularly polarized harmonics. So we can now control the polarization by changing the driving laser conditions. So I think the photon picture works very well, that since the high harmonic generation, we know we have to conserve energy and photon spin angular momentum. Conservation of energy just means that the X-ray we generate must be the sum of the visible or infrared photons we add to make it. Conservation of photon spin angular momentum means that that each X-ray photon must have left or right circular polarization, we can only grab one more red photon than a blue photon, since they have opposite chirality. And so what that means then is that we make a very exotic spectrum where what we do is, so the combined field of these counterpropagating visible driving light fields has a threefold symmetry. So what you do is when the combined laser field has a peak, you generate electrons, and they're illustrated here in green. And then the So the electron is born here, recombines with the atom, and then you get this burst of X-ray light. And in fact, this is an artist rendition. The actual physical light field is sort of crazy. I call this the crazy light fields because this is 1 femtosecond here. And so essentially the polarization is changing. The polarization frequency and amplitude are changing on a sub-femtosecond time scale. And we can get very nice agreement between our theoretical prediction and our experimental prediction. And essentially what we believe this is the most complex coherent light field measured to date. And essentially to measure it, we use a combined photoelectron spectroscopy combined with an infrared dressing field. So in the last 20 minutes or so of my talk, I'd like to talk about, so what does this new light source allow us to do? I'll just give one example. But we've looked at many different materials and many different applications. And because the light source has fundamentally new properties, it's giving us a tunable X-ray laser, which with short wavelengths and very short pulse durations. In any area we looked at, whether it be magnetic materials or looking at spin dynamics in magnetic materials or looking at the mechanical properties at the nanoscale, energy flow, or whether how materials change as you dope them, or imaging, or looking at electron dynamics because we have very short pulses. In all of these areas, we've learned something new about the material because we've had a fundamentally new tool. And so we'd like to say that we have a tabletop source that is complementary to the beautiful synchrotron and X-ray free electron laser sources that has benefits, the trade-offs for sure, but we have higher time resolution, very good spatial resolution. We have medium flux, but my favorite aspect is that it's a university scale apparatus, so a graduate student can have their own idea and go down and test it and make a discovery without having to write a proposal or wait 6 months. And so the rate of discovery is very high because it's only limited by our students' ingenuity, and they are really smart. So it's very complementary. And of course the beautiful synchrotron sources have the gorgeous, very, very engineered setup, and they're great for scientists who are, who know the important questions to be asked. Graduate students are still learning, and so often they can make a discovery by accident, and that's what we've seen quite a bit in our group. So last part of my talk then, I'd like to tell you about an aspect that our field has only recently looked into, because people thought initially these pulses are so short that the best application will be in looking at electron dynamics in molecular or in material systems, and we're absolutely doing that, and our community is publishing a lot of papers finding out many new things about molecular and material systems. But what was a bit unexpected was the spatial coherence. The fact that the beam is directed and laser-like turned out to have a very important consequence. And as is the case in much of science, when there's a convergence of a few different advances happening at the same time, you tend to have an opportunity to do something new and different. And this is happening now in the field of X-ray imaging and electron imaging, because if you look at X-rays, one great thing about them, of course, is that they penetrate. So compared with an electron microscope, you can look at a thick sample. And X-rays have these absorption edges that will tell you what element you're looking at, what its chemical state is, and what its magnetic state is. And the wavelength is also very short, so in principle, you should be able to image very small features. And if you've got high frequencies, you can also have very short pulses. But even in the case of static imaging, one thing that's limited X-ray microscopy was the fact that we didn't have a good lens. Excuse me. So essentially, X-rays are not refracted, so you have to build a diffractive optic to make a lens, to make a microscope. And because it's very hard, these are very hard to make and limited by our nanofabrication techniques, the best X-ray microscope that a normal person could have access, not the best place in the world, would give you an imaging capability that was about 10 times the diffraction limit. So 10 times worse. So because of that, scientists couldn't avail of the fact that the wavelength of X-rays, was very short, so that in theory you should be able to make a very high spatial resolution image, and it just wasn't possible. And so that meant that, and on top of that, they were extremely expensive, maybe $50,000 for a zone plate lens that might disintegrate as you walked across the lab. So just a hard technology. So typical spatial resolution that one could achieve in an X-ray microscope was about 25 nanometers, which for nanoscience and nanotechnology is actually too large a spatial scale now. All that changed around about, 5 years ago, but the origins were much earlier. That Sayre, Feinup, and others had proposed that if you have a coherent beam of light, you actually don't need a lens to make an image. You can take that beam of light and shine it on a sample, and then use a detector to collect the scatter pattern, and that means you have the amplitude of the diffraction pattern, and if you knew the phases, then you could make a simple Fourier transform and get the image. Of course, that is the question, how can you guess the phase? In initial work, the people put a constraint on the sample by requiring it was isolated. And in that case, what you can do is you can take your diffraction pattern and assign random phases so that you can take a Fourier transform and get an image. Of course, you won't have the image, the correct image, because you just guessed the phases. But if you knew the sample was isolated, you knew that any image that you retrieved in this region was just due to an incorrect guess of the phase. So you could set those amplitudes to 0, take another Fourier transform, keep the phases, and replace the guessed amplitudes with the experimental amplitudes. And then keep iterating until you hoped you converged. In this simple version of an isolated constraint phase retrieval algorithm, in general, the images were not very good. People made 200 different reconstructions and averaged them together to get the image of the sample, but of course no material scientist would want an average image of their sample. So for a long time it was an imaging science enterprise. And the other story I like about this particular work is that David Sayre proposed it in 52, and he was a co-author. This was done at Brookhaven, close to here, and he was a co-author on the first Nature paper to demonstrate this technique in 2D that was done at the Brookhaven lab. And exactly, and Sayre and Meow, exactly. And this phase retrieval is beautiful, and it's being implemented on all the high brightness synchrotrons and X-ray free electron lasers around the world. And in terms of our tabletop light sources, we were able to make them as stable, let's say, as a synchrotron source or a visible laser source, and that allowed the beam to be stable, because if the beam changes as you're trying to make an image, that's also that's an issue. And so we were able to really make very stable beams and engineer them. And then this is the paper, the full paper from 1952. I just like showing this to students because we certainly have to do more now. And of course, we love that last comment. The extension to 3 dimension is obvious. This is it wouldn't work this day. Okay, so For those of you who might not be familiar with phase retrieval, if we take an amplitude object, make a Fourier transform, we get an amplitude and phase. Of course, we don't have detectors that can measure phase. So let's say we'll throw away the phase, and then let's take retrieve the image, not knowing the phase, and then the image you get is just not very recognizable because you didn't use the right phase. There might be a few bunny ear type structures, but it really is not recognizable. Whereas instead, if you throw away the amplitude and you can guess the phase correctly, you get a much more recognizable image. There is an ambiguity here from this simple example. But what has changed everything now since 2011 are more powerful algorithms. So better ways of putting a constraint so that the algorithm can better guess the phase. And that's called tachography from Rodenberg and Maiden. So essentially you do, this is real data, so you scan a beam with about 80% of overlap as you scan the position. Then the algorithm has to reproduce an object that is consistent with a huge amount of redundant data. So essentially it over-constrains the problem. And that really has made a huge difference in the speed of convergence and the accuracy of convergence. And so they call this a tachography approach. Yeah. And so we can build a tabletop microscope now where we take our high harmonic beam, sometimes we monochromatize, or we select out a single harmonic order, and then raster scan with overlapping areas onto the sample. And essentially we can do that in both, this is a reflection mode microscope, this is a transmission mode, or a little artist rendition of the transmission mode microscope. And this was the first image where we thought this imaging technique really gives us something that we did not expect. So what it shows are titanium nanostructures on a silicon wafer. And the top image is the coherent diffraction phase image extracted by tachography. And the bottom image here is a scanning electron microscope image that we have at Jilla. It's not the best scanning electron microscope in the world, but it gives the typical contrast, let's say, in an academic environment. And what you can see if you look here, that we have much higher contrast images using the light CDI microscope than you have with the scanning electron microscope. And that's because in a scanning electron microscope, your contrast mechanism is that the electrons are bouncing off the material with different amplitude from different regions of the sample, whereas in our light-based CDI microscope, we're getting phase contrast, and of course the phase contrast is very high because our wavelengths are quite short, and so it gives us, and of course there's also amplitude contrast. So and we can make in this work it was the spatial resolution was 1.3 waves, so like 10 times better than you could make with the zone plate microscope. And the working distance is very high. It's 10 centimeters. So we can plonk this microscope on an optical table and connect a vacuum roughing pump to it. And it is very robust to vibrations because you're not worried, you don't have a very tight focus. What you just have to make sure that the scatter pattern, the scatter doesn't move from pixel to pixel on your X-ray CCD camera. And your pixel size is 13 microns. So it allows you to get very high spatial resolution on a system that you don't need a lot of like critical stability on. So it's another nice advantage. And we can make height maps. This is from the phase contrast, or compositional maps from the amplitude contrast. Because for those of you who have ever worked in the X-ray region, the UV region is notorious that a tiny amount of contamination will change the index or the reflectivity, but we can turn that to our advantage, because if there's a small change in reflectivity, then we know there's a composition or a contamination change. We can see buried layer, because of course even EUV light can penetrate metals, and so this is work where we took a nano pattern, over-coated it with 100 nanometers of aluminum, and then put that sample in a visible microscope, an AFM, and our high harmonic microscope before it was coated and after it was coated. And the interesting thing here is that the contrast between the copper and this is SiO2 changed in the overcoated sample compared to the coated sample. This should not happen. So here we were able to realize that there was interdiffusion of the materials going on in the buried interface, which is interesting to be able to read out without destroying the sample. The only other way to get at this is using an Auger probe or Auger sputter analysis, and that would destroy the sample. And then more recently, we've really pushed the spatial resolution down to sub-wavelength image resolution for the first time in the EUV or soft X-ray region. Essentially, we can get a spatial resolution of 12.6 nanometers at the technologically important 13 nanometer wavelength. EUV lithography was a project that started when I was a grad student at Berkeley. There was a consortium put together with Livermore, Bell Labs, LBL, and that was in the late 80s, early 90s it started, and it is only now being implemented because it took a long time to develop the 200-watt EUV source that's needed to make incoherent EUV source that's needed to print the chips fast enough to make it economically viable. And so it's sort of, and of course there's a need for metrology, we need it for science also, and there's a lot of very good optics available at 13.5 nanometers, and that was one of the reasons they chose that wavelength. So, and so we had to develop some additional algorithms, because if you try to image a periodic sample, the scatter patterns you get there's very little diversity in the scatter patterns, so it's hard for the phase retrieval algorithms to find the right object. But by adding in by forcing the algorithm to work with the real image of the illumination beam, we were able to have the algorithm work well even for periodic samples. And so in addition to increasing the spatial resolution, just the image quality has been improving over time. And this is thanks to the light sources, understanding how to engineer them better, make them more stable, understanding the algorithms, what are the right algorithms you need for the different phase retrieval and different samples. And so it's really been a convergence of technologies that we can now make something that is complementary to AFM and SEM. You can sort of think about the amplitude and phase images that we get with these EUV microscopes as giving, the phase image gives information similar to AFM, and the amplitude image gives you information similar to a scanning electron microscope. And so this is adding in the real picture of the beam into the loop, so that to prevent crosstalk between the algorithm has to retrieve the phase and amplitude of the illumination beam and the phase and amplitude of the object. And so unless you add in something to help the convergence in a highly periodic sample, you get an image of both the beam and the object that has a lot of noise. But if you add in some additional knowledge, a small amount of additional knowledge, then you get very clean reconstruction of both the illumination beam and the object. And this is our first movie where we heated a nanostructure, and now we want to take advantage of the fact this is not the most amazing movie in the world, but it still shows that we have the throughput so that we can actually watch nanostructure, heat and cool, and watch acoustic wave propagation. What we really want to do is make a dynamic image, for example, of a skyrmion excitation or a spin current or such, and this should be possible. It's taking a while. The um, uh, coherent diffraction technology, we have to optimize it for every sample at present, but we're developing a suite of tools we can bring um, to and one thing our students realize, because they try to completely model a nanostructure, heating, and then acoustic modes in the nanostructure, it's actually computationally too challenging to model it completely. So the funny thing, for all the pain it was to try to make this movie, because you've got to do tychography on every single step, it turns out it's less painful than a full 3D simulation of what was happening. So that was sort of an interesting. The other thing I wanted to show is that this can seem very academic. We've got the phase retrieval algorithms. We're using these quantum light sources. How does it actually stack up with what's out there commercially? And we were actually shocked when we did this calculation, because it turns out. My collaborator and husband Henry Captain, we've worked together for 30 years, but he was the entrepreneur in the family because I'm very academic, but. He did a calculation recently, and it turns out for EUV lithography, they need better metrology because many of the imaging tools are really near their limit. And so looked at what else was out there to do, say, a mask metrology. The mask is what they demagnify the pattern onto the chip to actually do the printing. And it turns out that the Zeiss Ames metrology tool is based on a laser plasma source and zone plate technology. And believe it or not, this harmonic metrology, when we actually did the numbers, it's actually 5 times higher spatial resolution, 10 to 100 times faster, and 1,000 times lower cost per image. So it's actually amazing. For a while, we were always thinking, this is really just of interest to physicists, but actually, it actually does much better than the conventional approach for an X-ray image. And this is another very, I mentioned it earlier, this was released in July of this year, that finally ASML believes that they have a business model for EUV lithography, that they actually, Cymer can make a bright enough illumination source that they can actually print the chips with EUV. And the other interesting sort of historical point is that Cymer is the laser company that makes the incoherent plasma sources, and they were spun off during the Star Wars era. So some good things came from it. And of course, just going forward, we're not at all limited to 12 nanometer spatial resolution, because it's easy. We know how to make these high harmonic sources at shorter wavelengths. And the one thing we do know from optics, that everything scales with the wavelength. So if you use, and since we don't have a lens, we just have to make the wavelength shorter, and our spatial resolution will increase. We have to do, we have to make sure we have oversampling and other things to make sure we can take full advantage of the coherent diffractive imaging, but that is possible. We should be able to get to under 5 nanometer spatial resolution in 3D using soft X-ray illumination. And earlier on today, I talked at the CCQM and was showing just a graph. I won't explain it, other than we can make measurements in time that's span from here 1 attosecond through a femtosecond through a picosecond. So this quantum light source technology has opened up a sort of a new capability of being able to really push temporal measurements well below a femtosecond, and actually being able to measure something interesting in materials. We're not just pushing electrons around. We can do that very, very well, but we can also actually apply them to look at interesting questions in material science. And similarly in the using this, of course, these measurements take advantage of the temporal coherence of the quantum light source and the imaging takes advantage of the spatial coherence of this light source. And of course, we want to bring them together. And we're very fortunate that on our third try, and after much pain, we were able to secure an NSF Science and Technology Center that we called Strobe. And we want to integrate electron microscopy, nanoimaging, and X-ray imaging, solve the common problems, many of which are, big data. If you want to make a functional imaging, then you need to do 3D imaging, and if you want to do it dynamically, that is a lot of data. So we need to do big data, algorithms, better detectors and sources, and combine them so we can make functional imaging of a non-crystalline material. So this would be the work of the center in techniques, detectors, data, and then, of course, working with other collaborators to apply these techniques to energy materials, quantum materials, disordered materials, and biological materials. And so the last minute or two, I know many of you in the room know the story of the MRI. Took 50 years to go from an observation to a commercial, and then eventually very critical medical imaging. Henry made the same timeline for harmonics. We're not saying at all that it would have the same impact of MRI. This was mainly for students saying that sometimes, you make a discovery and it's not obvious where the application will be. And for 20 years, it wasn't even apparent that with the harmonic, fundamental quantum physics, that there was any way to make a beam, a very good beam. But over time, our community was able to do that, and we're on the same sort of timeline as MRI. I know many of you in the audience might have seen this picture. This was the first commercial NMR spectrometer, and I know many of us have seen this little poster in the labs. This machine is subject to breakdown during periods of critical needs. There's a special circuit in the machine called the crisis detector, which senses the operator's emotional state in terms of how desperate he or she is to use the machine, and then creates a malfunction proportional to the desperation. And I think we've all experienced this in our PhD. I tell my students, your experiment will not work until you're about ready to either throw it out the window or just pull the plug. And that's just about when, you can, often you just have to tunnel through that, keep cool and say nice things, and nothing else will work. Okay, so I hope I've given a little bit of understanding of why do we say that these sources, they're a really unique quantum technology. Wasn't able to go into the details of the accuracy at which we can make these photons or time these photons or sculpt these photons, but it really, we have an ability to control X-ray fields in a way we never thought we would. It's just extremely precise. We don't know where the limits are, but we're already finding interesting things we can do with them, from basic science to metrology. And with that, I have to say a big thank you. This work was years of collaboration with my husband, an amazing group of students and fabulous scientists from all over the world. And I'd like to thank you very much for your attention.